In your car, dozens of tiny electronic components are silently making thousands of decisions every second. You don't see them. But if even one of them starts sending the wrong signal, your fuel economy drops, warning lights flash, and in some cases, your engine may not even start. Today we're going to break down the most important sensors used in modern cars, how they work, where they are located, and why even a small failure can create major problems. Before we begin, like and subscribe so this reaches drivers who want to understand their car instead of guessing. Number 1. Crankshaft Position Sensor. The crankshaft position sensor is one of the most critical sensors in your entire engine. If this sensor fails, your engine will not run. It is that simple. This sensor is typically mounted near the crankshaft, often positioned close to a toothed reluctor wheel attached to the crankshaft itself. As the crankshaft rotates, the teeth pass by the sensor and create an electrical signal. The sensor counts these pulses and sends the information directly to the ECU. From this data, the ECU determines two vital things: the exact position of the pistons and the rotational speed of the engine. It knows precisely when each piston reaches top dead center. That timing information allows the ECU to control when the spark plugs fire and when fuel injectors spray fuel into the cylinders. If the crankshaft position sensor sends incorrect data, ignition timing becomes inaccurate. The engine may misfire, stall unexpectedly, or refuse to start altogether. In many cases, the vehicle may crank but never ignite. Without this sensor, the ECU is essentially blind. It cannot synchronize spark and fuel delivery. That is why this small component is absolutely essential for engine operation. Number 2. Camshaft Position Sensor. If the crankshaft sensor tells the ECU where the pistons are, the camshaft position sensor tells it what the valves are doing. Both must agree perfectly. If they don't, the engine cannot run correctly. The camshaft position sensor is usually located on the cylinder head, positioned near the camshaft. Its job is to monitor the exact rotational position of the camshaft. Since the camshaft controls the opening and closing of intake and exhaust valves, this information is critical for precise combustion timing. The ECU compares signals from both the crankshaft and camshaft sensors to ensure proper synchronization. This coordination allows for sequential fuel injection, meaning fuel is delivered to each cylinder at the exact right moment. It also ensures ignition timing is accurate down to milliseconds. If the camshaft sensor fails, you may experience extended cranking, rough idling, reduced fuel efficiency, or sudden engine shutdown. In many vehicles, the engine may enter a limited performance mode to prevent damage. When the ECU detects a mismatch between crankshaft and camshaft signals, it knows something is wrong. And when these two sensors fall out of sync, performance drops immediately. Number 3. Mass Airflow Sensor. Every time you press the accelerator, your engine demands more air. But how does the engine know exactly how much fuel to inject to match that air? That decision depends heavily on the mass airflow sensor, commonly called the MAF sensor. The MAF sensor is typically located between the air filter box and the intake manifold. All incoming air must pass through it before entering the engine. Inside the sensor is either a heated wire or film element. As air flows across this element, it cools it down. The sensor measures how much electrical current is needed to maintain a specific temperature. From this, it calculates the precise mass of air entering the engine. The ECU uses this data to determine the correct fuel injection quantity to maintain the ideal air-fuel ratio. Too much fuel wastes gasoline and reduces efficiency. Too little fuel can cause misfires and poor performance. If the MAF sensor becomes dirty or fails, the engine may hesitate during acceleration, idle roughly, or consume excessive fuel. In some cases, it may even stall. A contaminated MAF sensor can slowly degrade performance without triggering immediate warning signs. And when it sends incorrect data, every combustion cycle is affected. Number 4. Manifold Absolute Pressure Sensor. While the mass airflow sensor measures the amount of air entering the engine, the Manifold Absolute Pressure Sensor, or MAP sensor, measures the pressure of the air inside the intake manifold. Together, these readings allow the ECU to understand the engine's load in real time. The MAP sensor is usually mounted directly on the intake manifold. It detects the pressure created by incoming air as well as the vacuum generated during engine operation. When you press the accelerator, manifold pressure increases. When you release it, vacuum rises. The sensor converts these pressure changes into electrical signals and sends them to the ECU. Using this data, the ECU calculates how much fuel to inject and how to adjust ignition timing. Higher pressure typically means more air entering the engine, requiring more fuel. Lower pressure means less fuel is needed. If the MAP sensor provides incorrect readings, the engine may run too rich or too lean. Symptoms can include poor acceleration, black exhaust smoke, hard starting, or reduced fuel efficiency. Because the MAP sensor directly influences fuel delivery, even slight inaccuracies can affect performance and long-term engine reliability. If you appreciate clear breakdowns like this, take a second and hit the like button. It helps this channel reach drivers who are tired of guessing and want to actually understand how their vehicle works. Number 5. Knock sensor. Inside your engine, combustion is supposed to happen in a controlled, precise explosion. But when fuel ignites too early or unevenly, it creates a sharp metallic noise known as engine knock. Left unchecked, knocking can damage pistons, bearings, and cylinder walls. That's where the knock sensor steps in. The knock sensor is typically mounted on the engine block, where it can detect vibrations directly from the combustion chambers. It contains a piezoelectric element that generates voltage when it senses high-frequency vibrations. These vibrations are characteristic of abnormal combustion events. When knocking occurs, the sensor immediately sends a signal to the ECU. In response, the ECU adjusts ignition timing, usually by slightly retarding the spark. This reduces cylinder pressure and prevents further knocking. The process happens in milliseconds and protects the engine from serious internal damage. If the knock sensor fails, the ECU may not detect harmful detonation. Over time, this can lead to reduced performance or even engine failure. In some cases, the ECU may default to conservative timing settings, causing noticeable power loss and poor fuel efficiency. The knock sensor quietly protects your engine under heavy loads, high temperatures, and aggressive acceleration. When it stops working, damage can begin without warning. Number 6. Coolant temperature sensor. Your engine generates intense heat every time it runs. If that heat is not controlled, internal components can warp, seize, or fail completely. The coolant temperature sensor plays a key role in preventing that disaster. This sensor is typically located near the engine's coolant passages, often close to the thermostat housing or cylinder head. It constantly measures the temperature of the engine coolant as it circulates between the engine and radiator. The sensor sends real-time temperature data to the ECU. When the engine is cold, the ECU enriches the fuel mixture to ensure smooth starting and stable operation. As the engine warms up, the ECU gradually adjusts the air-fuel ratio for optimal efficiency and performance. The ECU also uses this data to determine when to activate the electric cooling fan. If the coolant temperature sensor fails, the ECU may receive incorrect temperature readings. This can lead to hard starting, poor fuel economy, overheating, or the cooling fan running continuously. In severe cases, the engine may operate in an overly rich condition, washing excess fuel into the cylinders. Because temperature directly affects combustion efficiency, even small inaccuracies from this sensor can create noticeable performance issues over time. Number 7. Fuel temperature sensor. Fuel may look the same in your tank year-round, but its properties change with temperature. As fuel warms up, it becomes less dense. When it cools down, it becomes denser. That small change in density affects how much energy is delivered during combustion. The fuel temperature sensor exists to account for that difference. This sensor is commonly located either inside the fuel tank as part of the sending unit or mounted near the high-pressure fuel pump in some vehicles. It continuously measures the temperature of the fuel and sends that information to the ECU. The ECU uses this data to adjust fuel injection timing and quantity. Warmer fuel may require slightly different calibration compared to colder, denser fuel. These adjustments help maintain consistent combustion efficiency, power output, and emissions control. If the fuel temperature sensor sends incorrect data, the air-fuel mixture may become inaccurate. This can result in rough running, reduced performance, increased emissions, or difficulty starting in extreme weather conditions. While many drivers never think about fuel temperature, the ECU constantly monitors it to maintain stability. A small error from this sensor can gradually affect engine smoothness and long-term efficiency. Number 8. Crash sensor. Some sensors are designed to improve performance. Others exist to save lives. The crash sensor belongs to the second category. Crash sensors are small but highly sensitive electronic devices positioned in critical areas of the vehicle. They are typically located behind the front bumper, along the frame rails, and inside the side pillars or doors. Their job is to detect sudden deceleration or impact forces that indicate a collision. When an accident occurs, the crash sensor measures rapid changes in speed and structural movement within milliseconds. It immediately sends a signal to the airbag control module. The control unit analyzes the severity of the impact and determines whether airbag deployment is necessary. If deployment is required, the inflator system activates almost instantly, usually within 25 to 50 milliseconds. The airbag fills with gas and provides a cushioning barrier between occupants and hard interior surfaces. If a crash sensor fails or sends incorrect data, airbags may not deploy during a serious collision. For this reason, the system continuously performs self-checks, and any fault typically triggers an airbag warning light. This sensor works silently, waiting for a moment no one hopes to experience. Still here? Then you're not just driving your car, you're learning how it thinks. And that knowledge saves money. If this breakdown is helping you see your vehicle differently, subscribe to Car Failure Files and turn on the bell. We focus on the components that quietly control everything long before a warning light shows up. Number 9. Wheel speed sensor. When you slam the brakes at high speed, your vehicle must slow down without losing control. If the wheels lock completely, steering becomes impossible. The wheel speed sensor prevents that from happening. Each wheel is equipped with a dedicated speed sensor, typically mounted near the hub assembly. These sensors monitor the rotational speed of each wheel by reading a tone ring or reluctor ring attached to the axle or hub. As the wheel spins, the sensor generates electrical pulses that correspond to wheel speed. The data is sent to the ABS control module, which constantly compares the speed of all 4 wheels. If one wheel begins to slow down much faster than the others, it indicates potential lockup. The system responds instantly by reducing brake pressure to that specific wheel through hydraulic valves. Once traction is restored, brake pressure is reapplied. This rapid cycle of applying and releasing brake pressure can happen multiple times per second. It allows the driver to maintain steering control while braking hard. If a wheel speed sensor fails, the ABS warning light usually appears. In some cases, traction control and stability systems may also become disabled, reducing overall vehicle safety. Number 10. Parking sensors. Modern vehicles are larger than ever, and blind spots have become a real concern, especially during tight parking maneuvers. Parking sensors are designed to reduce that risk and prevent low-speed collisions. These sensors are usually embedded within the front and rear bumpers. Depending on the system design, they operate using ultrasonic waves or electromagnetic detection. When reverse gear is engaged, the rear sensors activate automatically. In many vehicles, front sensors activate when moving slowly or when the brake pedal is applied. Ultrasonic parking sensors emit high-frequency sound waves that bounce off nearby objects. The reflected waves return to the sensor, and the system calculates the distance based on the time it takes for the signal to return. The closer the object, the faster the signal returns. The system then provides visual alerts on the dashboard display and audible warnings that increase in frequency as the vehicle approaches an obstacle. If a parking sensor becomes damaged or blocked by dirt, the system may give false warnings or fail to detect obstacles entirely. While these sensors operate at low speeds, they prevent costly bumper damage and improve overall maneuvering safety in tight spaces. Number 11. Rain sensor. Driving in heavy rain demands quick visibility adjustments, constantly changing. Wiper speeds manually can distract the driver at the worst possible moment. The rain sensor eliminates that distraction. This sensor is typically mounted on the inside of the windshield near the rearview mirror. It works using infrared light technology. The sensor emits an infrared beam onto the windshield at a specific angle. When the glass is dry, most of the light reflects back into the sensor. When raindrops accumulate on the surface, the reflection pattern changes because water alters how light refracts through the glass. The system detects this change and immediately signals the body control module to activate the windshield wipers. The intensity of rainfall determines how frequently the wipers operate. Light rain triggers intermittent wiping, while heavy rainfall increases speed automatically. Many systems also factor in vehicle speed, increasing wiping frequency when driving faster. If the rain sensor malfunctions, wipers may activate unnecessarily or fail to respond during rain. Though it may seem like a convenience feature, it significantly improves visibility and driver focus in sudden weather changes. Now you've seen how many sensors operate behind the scenes every second your car is running. When one of them fails, performance drops, fuel economy suffers, and safety systems can shut down. If this helped you understand what's really happening under the hood, hit the like button and subscribe to Car Failure Files. And in the comments, tell me which sensor surprised you the most.